Thank you for the invitation. Because of the visa issue, I cannot attend in person. I cannot attend the conference in person. However, I'm still happy to share my research with you online. Hello, everyone. My name is Weiqi Wang from University of Victoria. This is a joint work with Simone, Nick, and Samir. Today, I will show how to solve high-dimensional PDEs without big grid using periodic pins and compressive Fourier collocation method. You can access this paper from the QR code here. So let's begin. First, I want to talk about the challenge and our model. High-dimensional problems are hard because the computational cost explodes with the dimension. Like D here, on grid unknowns grow like the number of points to the power of D and to D. That's the curse of dimensionality. This effect shows up in like the problem in many domains. Our model solve a diffusion reaction equation on a periodic box, considering a smooth diffusion coefficient A, and which is always greater than zero, and a positive reaction term rho u. Rho is positive, and known on right hand side F. We can write this PDE as Lu equals to F. We use this periodic setting as a toy problem to simplify the proof and difficulties. Periodicity let us use Fourier basis, which match the boundary conditions automatically, so we do not have to worry about the boundary conditions. It also makes sampling simple. We can pick random points on the torus T to a D without worrying the edges. The goal today is pretty simple. We want to avoid huge grids and keep the number of samples small and still solve the PDE accurately. So here are the two ideas to avoid big grids. The first one is the physics-informed neural network. So the idea is that we train a neural network, so the equation residual at random points is small. So there's no mesh here. We choose collocation points xi and plug the neural network into the PDE and compute the residual showing here. And we use back propagate or like some people call auto differentiation to calculate the grade in this minimization problem. If the structure of the solution is unclear, this is safe and flexible choice. And then the second one is compressive Fourier collocation method in 2024. In this method, we try to write a solution as a small number of periodic wave, and uh, we build a short list of frequencies, like in lambda here, and solve a small linear system that matches PDE at collocation points xi. And then after we solve this, yeah, we try to find a sparse approximation for a sparse solution for this system, and then we get only the important frequencies using sparse recovery. If the exact solution is sparse in Fourier basis, this method can be very strong. So both of them avoid heavy grades. The first one, the pins learns a smooth function, while the compressive Fourier collocation finds key frequencies. So like the one last comment here, we can think the pins like fitting a smooth surface that obeys the law at every sample point, and think the compressive Fourier collocation is like mixing a few pure tones to match the song of the PDE. Yeah, that's a basic idea of these two methods. And now I would like to introduce what's new in our work. The first point, there are 3 points. The first point, we have a practical existence theorem for periodic physics in for neural net pins. It gives a sample rule and neural network size, so you know the bound that how many points to take and how big the neural network should be. Mm. And then we develop an adaptive greedy method for compressive Fourier collocation. It grows the Fourier set on the fly, looking only at the age of the current set, then grow the set accordingly. This saves memory and computational cost. And we did some numerical experiments up to d to the 20, and we made some comparison between pins and compressive Fourier collocation. So let's go into the first method, periodic pins. So let me show you the pins we are analyzing. So the architecture is pretty simple. The neural network starts with a periodic layer. It uses cosine features with trainable phases. So the output of the neural network is always exactly periodic. So we do not have to fight the boundary conditions. Then comes the standard hidden layers, which are simple, like the connected, I mean the MLP, the multi-layer pattern, a composition of the linear and the linear transform and nonlinear activation, followed by a linear output. Yeah, that's our pins architecture. And then the input are variable x, points in the domain, and the output is the solution value of the PDE, like the UX here. And then training is quite straightforward. We choose random collocation points, xi here, and then we plug the neural network into the equation like that. And then we minimize the mismatch between the result from neural network and the right-hand side of the equation. And then the derivative of the in the operator is handled by automatic differentiation. And then we go to the next one. Before the theorem, there's one more ingredient we need, which is the hyperbolic class. On the left, I'm showing a hyperbolic cross set in 2 dimensions. And here on the right is a definition of the hyperbolic cross set. Actually, the idea of the hyperbolic cross set is that we keep frequency index where not all coordinates are big at once. If one coordinate is big in one direction, the others stay small. This make a thin hyperbolic cross shape instead of a full grid. uh, I mean, this is a smart way to sample the frequency space. So the reason we use hyperbolic cross is that this set is much smaller than full grid, and its size grows like n times the power of log n. So it scales better as the dimension d grows. And actually, it still captures key behavior in many smooth or anisotropic problems. So, so we use it by pick our Fourier frequencies from this set, and it gives us a compact dictionary for the theorem, and also it gives us a good search space for the compressive Fourier collocation method, which we will talk about later. Now, this is our main theorem. So the theorem, actually, I do not want to like read through all of these notations in this slide, but only give a brief idea. The theorem says that if the true solution can be well described by a small number of those Fourier modes, and if we take enough random sample points like that, then a trend periodic pins exist with small error. I mean, the error is given by these three terms. The first term is the best S-term part. So this is a price of only using as like important frequencies in Fourier basis. And a truncation part, this is a price we are using like a finite dictionary lambda instead of the like a full space. So, and then the third term is the training or the error comes from noise. So this part of error comes from sampling and optimization. And and we also get the explicit neural network size. Uh, the depth of the neural network is like log of the dictionary order n here. I mean the dictionary order of the hyperbolic cross set, and the width grows mildly with the dimension and the order n shown here. So we have a practical receipt, like how many samples we need and how big the network we need. So I can just go through the symbols. The S is like the number of the important frequencies we need, like the sparsity. The N is how many frequency we allowed overall, I mean, which is the cardinality of the index set lambda. And polylog n means a polynomial of n, which is independent to dimension d, which grows slowly, and delta here is a success chance. Yeah, I mean, since our sample is choose randomly, so we still have a probability to fail. And then actually the delta is a small one. Is the small failure probability. Okay, so I want to say more about these three error terms. So why do we get exactly these three like pieces of errors? This actually comes from the proof of the theorem. So actually, let me briefly explain the proof idea. So the first step, we write the target function, I mean the solution of the PDE, as a short Fourier sum taken from the hyperbolic cross set. And then we assume only a small set of frequency really matters in this PDE solution. And then the second step, with random sample points and the residual loss, training the last layer of the physics info neural network looks like a sparse recovery problem. So we can use some like simple tool like L1 style regularization in the loss function to enforce the sparsity. And then the step three is the sparse approximation theory. Uh, so some known results say that the coefficient error is small when we have enough sample, and when we move back to the functions, we add a truncation term because we use a finite set lambda instead of uh, the entire space. This gives us the first term here. And also there are error caused by training error or noise. I mean, the noise is like the noise of the linear system. So sometimes when we testing the PD residual, they may have some like the truncation error at each collocation point. So we have the second term here. So these three steps explain the three parts of the final error bound. Let's point to, I mean, let me go back to the error terms uh to make the correspondence. So like where each terms comes from. The first one, the best S term error on lambda is written like that. So it's like even we keep only S frequencies, we may not match the truths exactly. So this is the price of the sparsity. So I mean, this is step three, sparse approximation theory. And then there are truncation error. Like we work on a finite hyperbolic cross set, not of frequency. So this gives us uh the error like that. So this is from this, so this error comes from step one and maybe step three as well. I mean, because it has some sparsity here. And the training error or noise, it comes from the mm, step two, because we sample at random point, we solve an optimization problem. So with more sample and better optimization, this part shrinks. And then now I want to compare our theorem so what's the difference between our theorem and the commonly used universal approximation theorem? So actually, the universal approximation theorem says a big network can approximate any continuous function on a compact set, but it gives no error rate, no rule for how many samples, and no guarantee of the training will be in I mean, or like no guarantee that training will find the good parameters. It will also ignore the PDE structure. However, in our theorem, this is a task-aware process. It uses PD residual, it gives a rough sample rule, and the bounds on the neural network size. It splits the error into three visible parts. So you will know what limits you in training neural network. Here are the caveats we have in our theorem. The first, we work on a toy problem for sure. And then this gives us a steady periodic diffusion reaction equation on d-dimensional torus only. And we did not consider time-dependent PDE and only mild oscillation in the coefficient. We are assumptions, for example, in A, and the bounds we have are not too tight. There's no, and also we did not analyze the error from the optimizer, like the gradient descent dynamics. Okay, so this is our theorem. So let's switch to the compressive method, compressive collocation method. So the idea of the compressive collocation method is we write the solution as a few periodic wave. We do not build a huge list first. We grow the list as we go. So the first idea is that we would like to keep the lambda as a lower set. So what's a lower set? We can have a look at the picture. We can think of a grade of the frequency indices. If a big index is in the set, then all the smaller ones that sit under it must also be in the set. So that's the meaning of the lower set. So in 2D, it's like everything under the like the red curve here must be in the set. The thin boundary of of that shape, the thin boundary like showing in the red dot are the reduced margin. And then, yeah, which is like the boundary or edge of the lower set. So we only scan the boundary. We only scan the boundary for new candidates to add to our Fourier basis. I mean, for lambda. So here is the process. We start from a tiny set, like starting from an empty set or like origin, and we look at the age and then like some adjacent points, And we pick the frequency that best explain the current residual, and we add this into our Fourier index set. And we also add all of its reflections so the set stays lower. I mean, we want to make sure there's no hole in this set, and refit all coefficients on the active set and update the residual. And we repeat this process until we meet the computational budget. Okay, so there are several benefits for this method. The first, we never do solve this linear problem in a huge hyperbolic set. We only touch the edge instead of the entire set. And also it's stable because it closing under the lower structure, and then it usually will not miss any important frequency. So the fit it will be robust and less shaky. And also it can extend to a high dimensional D. Because the size of the edge stay much smaller than the full candidate list, or even like the cardinality of the hyperbolic cross set. So here is a detailed algorithm. So the first, we start with no frequency, and then we set the residual is a mismatch with the data. And then we scan the reduced margin. We look only at the boundary, which is we search the reduced margin, and then we score the candidate. For each candidate, we measure how much it explains the current residual. This we use the simple correlation test here, and then we make a greedy selection. By choosing the top one, and then we add all sign reflections of the best candidate to make sure the index set lambda preserve the lower structure, and then we repeat the coefficients. We solve the least square on the new index set, and then after that we repeat it like k times, and then until the budget k is reached. Okay, so this is the Fourier collocation method using adaptive lower OMP. OMP means orthogonal matching pursuit. This is a variation of orthogonal matching pursuit algorithm. So now let's go to the numerics. So we test three examples. The first example is a product of sign. This is very sparse in Fourier space. We want to check if we can find a few key frequencies for this algorithm. And then the second example is the exponential of two sign function. So this will provide us a smooth function with only two variables. So strong anisotropy between different variables. And the third one, we test the exponential with all dimension. Actually, the weight decay with the index. I want to check the function that is active on almost all dimension, in all dimension. And the periodic pins we use has a small periodic layer, like a periodic layer with 11 nodes, and we have three hidden layers. Each of them has 3 nodes. And this is for the hidden layers, and the activation function is tanh. And we train a neural network about 30,000 steps, so usually it's adequate for these examples. And we use random collocation, and we calculate the relative error through, for example, 25 random runs. Yeah. And then let's see what happens if we change the number of samples. Okay, so these parts are for dimension 6. This curve shows error over training steps for different sample size, like 1,000, 2,000, and 3,000. Usually in this training process, we observe a fast drop very early and a slow approach to a floor. More samples usually give a lower floor and more stable training. The, the gain depends on the example, but the trend is clear. So this match the theory. The training or noise, the training error or the error from the noise uh, start shrink for with more samples. And then let's see how dimension change the samples. How the dimension change the samples we need. Here we fix the training budget, like 30,000 epochs, and then we look at the final errors versus the number of the samples for for dimension 6, 10, and 20. So to reach the target like 1%, the required samples grows about linearly in respect of dimension. So it's like in dimension 6, we need like 2,000 samples to converge. And then for 10 dimension, to 10 dimensions, we need like 4,000 to converge. And for 20 dimensions, we need like 80 sample points to converge for pins. So we can see this, uh, so they are about linearly with the dimension. So they do not explode exponentially. So in the pins, we can see that pins is the curse of dimensionality. And then after that, we do a quick check on architecture sensitivity. So we vary the number of periodic features and like the depth and width ratio, and also the number of nodes in periodic layers. And then past about 10 periodic nodes, there's little gain in accuracy. And also, adding more layers in hidden layers also doesn't help much. So the periodic pins layer method is not very sensitive to this choice, which is good for practice. So now we compare the physics in neural network with the compressive Fourier collocation method. Okay, so I compare the L to L uh for both method for the three examples. And then when the solution is sparse and anisotropy in Fourier space, so like in example 2 and 3, the compressive Fourier method can reach lower error faster and much more accurate. However, in example 1, since even though we only have like one Fourier basis. However, the solution doesn't follow the like a lower structure. So the compressive Fourier collocation has a worse performance compared to pins. However, pins are more robust when the structure is unclear, and it still converge for and still converge for all of this example, and also the computational cost scale mildly with in respect of dimensionality. Okay, so yeah, actually this is like the summary here. So I will end with the open problems. So here are some future works. The first, I would like to analyze some time-dependent PDE, and then with some complex boundary conditions or initial conditions. And also, if possible, actually the theorem itself is pretty messy now, but I don't know if we can like weak the assumptions on uh, these parameters in the PDE or tighten the theory. And in and a promising direction for the like machine learning theory is analyzing the training dynamics of this like gradient descent based method. And also, yeah, I mean, I as I mentioned, we need to consider boundary and initial conditions as well. Yeah. Okay, so thanks for your listening. I'm happy to take questions. Or I mean, if you have any other questions, you can send me like message or just email me at wichuang93 at gmail.com. And yeah, thank you for the listening. And these are a few reference we used in this slide.